Hi, I'm Jason West from the University of North Carolina. We're not meeting in person today because of a global epidemic. But by the time we get out into the middle of the 21st century, I think that pandemic will be a minor footnote in history. We will, by that point, be dealing with what I think is a bigger problem of climate change, with its many different types of effects on the world around us. I want to talk with you today about how this challenge, looking out over the next century, addressing climate change, relates with air pollution. And I'll make the case that we have endured over the course of the 20th century and going into the 21st century, a plague of air pollution that is really coming about mainly from fossil fuel use. My talk today will be in part a review of history of these different problems, but looking forward to the next century as well. But along the way, I'll also highlight areas of research from my lab where we've used computer models to drive assessments of air pollution, health impacts, and energy policies. Great. So let's start with the Industrial Revolution. This is England in the late 19th century. You see factories burning coal. What might be less obvious to you here, we see what I presume are people's homes and businesses, which are also likely burning coal for home heating and cooking. So certainly it's been the case through time that we've endured very high levels of air pollution, at least in some very industrialized places in the world. And the transformation that took place from the Industrial Revolution is illustrated here from a world that was fueled by biofuels, so wood, into the 20th century where we started using coal, then oil mainly as a transportation fuel, then natural gas, as well as solar, nuclear, renewables, and hydropower, which together are really a small fraction of the total energy use that we have today. This transformation in our ability to use energy productively has really transformed the world around us and enabled new possibilities for humanity in ways that I don't have to recount. But it's certainly one of the important stories of the 20th century. But it leads us with a couple of important problems, being climate change and air pollution. Let's look more at air pollution and health. This is Donora, Pennsylvania, not a very big town in the United States, but in 1948, it had the most severe air pollution episode in probably US history. 20 people died. A third of the town became sick. This is one of the photos during the daytime with the streetlights on. A similar photo from 1952 in London, also during the photo is during the daytime. In this case, there was a huge population exposed to the high levels of air pollution. So we had an episode here, this is day by day, lasting about a week long with very high levels of air pollution. And we see daily counts of deaths, so that about 4,000 people are said to have died during this episode, but others have argued that the number is actually much higher. This is then the 1950s, going to Los Angeles, when a new form of air pollution emerged in terms of our understanding, that is photochemical smog and ozone air pollution. And now we understand that ozone is pervasive throughout the world, but this was where our understanding of it sort of began. If we go to the 1970s, then in 1970 in the United States, we passed the Clean Air Act. And in 1990 were the very important amendments to the Clean Air Act that really had a substantial role, gave substantial ability to the United States Environmental Protection Agency to bring down concentrations. And as a result of those regulations, we have improved our air pretty considerably. The blue line here is SO2, which is mainly from historically from coal combustion. And you see that it's decreased actually by about 90% over this period. It itself is an air pollution. is an air pollutant, but its really important effect is that it leads to sulfate particles that are a part of PM2.5, and you see PM2.5 also going down here. From a health point of view, this is really a success story, we could say. And over the course of this period, it's really certain that this decrease of concentration has avoided tens of thousands or hundreds of thousands of deaths prematurely in the United States. And while this was going on in the United States, of course, Europe was doing something similar. This is another view for the US, looking from a satellite at NO2, showing that dramatic decrease of concentration. How about the rest of the world then? So this is Beijing during what was known as the airpocalypse, a view from space. These are clouds at the bottom here, but this shows the very high levels of air pollution over Beijing and the surrounding areas, with air pollution particles streaming out through the mountain passes, showing up very vividly over the bright snow surface underneath. There were very high levels of air pollution associated with this episode. This is what it looked like at ground level in Beijing. China has probably turned the corner now to cleaner air and I'll show you a picture of this later, from the early 2010s. How about the rest of the world? And we certainly have severe air pollution problems in important places where people live here, India and Bangladesh. And as we look over, this is one of the pictures from Delhi, from pre-COVID lockdown to during the COVID lockdown, how much the air improved. And as we look around the world, we look at places like Southeast Asia and Africa as places where air pollution may continue to get worse before it starts getting better. Where do we stand today? So today, about 95% of the world's population lives in areas that exceed the WHO guideline for ambient PM2.5. It's not just polluted countries in the world, it's really the world's population by and large is breathing polluted air. And we know that most of that, about 71% here for PM2.5, is estimated to come from fossil fuel combustion. So fossil fuel use is a driving force for severe air pollution, as it is for climate change. In the 1970s, we knew that air pollution was detrimental for health from a variety of reasons. We saw the London smog case before, but in the 1970s, then we had daily time series studies in epidemiology that related air pollution with daily deaths. This Harvard Six Cities study in 1993 then was very important for advancing that understanding by showing that people over the course of their lives, through their chronic exposure to air pollution, die prematurely. So these are the 6 cities, from very polluted here to very clean here. And you see this very strong relationship between the risk of dying and the average concentrations that people were exposed to. This led to a conclusion here that about 60,000 or so die prematurely each year due to exposure to ambient air pollution. And based on what we understand today, that's certainly in the right ballpark. So what we'd like to know is, what is the global population breathing? And what is the global effect of air pollution on health? And before about 2010, we didn't have a good answer to this question. And the reason why was because we don't have enough monitors present to know what people are breathing in many parts of the world. So there's dense monitors and monitoring networks in North America, in Europe, in Japan and South Korea, but elsewhere that hasn't been the case. So the question then becomes, what are people breathing? Or to put it in more scientific terms, what are ambient ground level concentrations at fine spatial resolution? That's what we'd like to know. About 2010, then we got 2 breakthroughs. One was in the use of satellites to look at PM10 from space. Satellites observe aerosol optical depth, but you can then translate that to estimates of ground level concentration. And that's what was done here. And so this became an important input to the global burden of disease exercises. And the other breakthrough was the use of computer models of the atmosphere. So my lab in 2010 was the first to use a global model of the atmosphere to estimate how many people die prematurely due to exposure to ambient air pollution all around the world. And here, this was our second study doing this type of thing. This was led by Raquel Silva, my PhD student. She's using then a bunch of different computer models, asking what the effects of those are on of the concentrations that each model estimates on exposure and therefore health. Raquel found that we get a different answer when we use different computer models, but overall, the average of these is about 500,000 ozone-related deaths per year. For PM 2.5, then about 2 million deaths per year prematurely. And these are where those deaths occur located. It's where the people live, as well as where it's polluted. And we had estimated that about half the global total PM 2.5 related deaths occur in East Asia, which is mainly China. The best estimates that we have today come from the Global Burden of Disease 2019 study, and I'll summarize those here. So they had estimated in 2019 about 4 million deaths per year related to ambient PM 2.5, 400,000 or so related to ozone. The third factor here is household air pollution from solid fuels. That's burning of wood as well as coal or other solid fuels in especially low and middle income countries all around the world, often in kitchens and often with very poor ventilation conditions. So it's often women and children that are in those environments, and they'll spend hours a day breathing extremely polluted air. If we add these three together, that is about 6.7 million deaths, or about 1 of every 8 or 9 deaths that happen globally. One of the nice things about GBD is it lets you compare different risk factors, which are listed here. These are the most important risk factors for health globally. And on that list, air pollution is the only environmental risk factor to show up. So GBD has shown, starting in about 2010, because we didn't have estimates of global air pollutant concentrations before that, that air pollution is the most important environmental risk factor for health. And look at the other things around it. There are things that many of us would appreciate, like obesity just below it, as being very important for health. And we might be surprised to see that air pollution is right there in that list. I'm in this talk emphasizing the very long-term view. So we can use GBD. They had done estimates back they had done 2019, but going back to 1990, and if we add up over that period, that's about 100 million deaths that are attributable globally to ambient air pollution. Certainly a very important problem. To put that into context, I've put this, taken this 6.7 million deaths from air pollution and compared it to a bunch of different other causes of death. And if you add up all of these, you get about the total from air pollution, again, underscoring its importance on a global scale. So before I leave the GBD studies, I want to say a little bit about our other contribution to those studies, which are that the estimates for ozone were, ozone-related deaths were created using our estimates of ozone ground level concentration globally. We did that first for GBD 2017, led by Kailan Chang, using the TOR compilation of global ozone measurements, the biggest that's ever been put together. And CCMI are a bunch of computer models, and we combine those together through a statistical data fusion to estimate this estimate that was used by GBD 2017. Here you see that the models are biased high, so part of our estimate is to reduce that bias, but then Kailan's methods found the set of models that best reproduces observations in each world region, and that was driving this global estimate. We improved upon that for GBD 2019 by estimating ozone concentrations in each year individually. We added additional observations in computer models, including this new network that's popped up in China that we didn't have available before. We're using BME data fusion methods to smoothly weight observations across space and time, and we've provided fine resolution output by scaling relative to a global computer model that was run at very fine spatial resolution. And so this movie shows our estimates year by year of ozone concentrations. The BME method was led by Mark Sayre, who's my colleague at UNC, and implemented by graduate students Marissa DeLange and Jacob Becker. We found that using the BME method, we match observations at monitoring stations, and the influence of an observation then drops off in space and time according to its covariance. Far away from observations, the model then goes toward the multi-model composite that was created using Kailon's methods. Okay, so this was used for GBG 2019. And this is one look at the output that was created. These are population weighted concentrations here shown going up globally. Some regions are going down, so like North America and Russia have gone down historically, but this global increase is concerning, and where we see that increase happening is East Asia, which includes China, South Central Asia, which includes India, as well as Africa. So those three regions are driving this global increase in exposure to ozone, which of course is concerning looking to the future. Okay, so I'm a computer modeler, and my interest in using computer models is to, in part, use those computer models to understand exposure, as we did for the global burden of disease, but also to ask questions about what we could do to change air pollution and therefore improve health or have other effects on beneficial effects on the climate system. So that is to inform policy choices. And the first study that I had that did that is shown here. It was together with Denise Mazeral, who's also part of this conference. And at that time, it was somewhat new that methane was understood as not only a greenhouse gas, but that it also contributes to the global background concentration of ozone. So we thought that was interesting and asked the question, could we justify in cost-benefit terms reducing methane to manage ozone air quality, reducing everybody's ozone all around the world at the same time? And to address that question, we used our global computer models, put into it a 20% reduction of global human-caused methane emissions. That gave us then a change in ozone concentration. We overlaid that on the global population and estimated that we avoided 30,000 or so deaths in 2030 due to that reduction in ozone. When we put a dollar sign associated with those lives saved, we found that the benefit to global health outweighed the cost, that we could actually justify this entire 20% global methane reduction by the benefits to air quality and human health, apart from other benefits that you would get from slowing down climate change. What surprised me at the time was this was one of the first times, certainly if not the first time, that anybody had used one of these global atmospheric models of looking at global air pollution to drive a health impact assessment. And the direction of my lab's research in the time since then has really gone in this direction of looking for other applications. And there's a growing global community of scientists doing this sort of work. Here's one example of that. So this is again Raquel Silva, where we not only looked at the effect of air pollution on total deaths, but attributed that to different sectors. So what's shown here is the fraction of total deaths that are attributable to emissions from different sectors, showing that energy is really important in the United States, industry in China, transportation in the US and Europe, and elsewhere in the world, such as India or Africa, residential and commercial emissions stand out as being very important. Okay, so let's take a step back and talk about how broadly air pollution and climate change are related, and then I'll show you some more examples of the work we do in my lab. So first, several air pollutants affect climate. So ozone's a greenhouse gas. Aerosols, which is known as particulate matter in the air pollution world, by and large have a cooling influence on the Earth. Secondly, changes in climate may affect air quality. I'll talk about that next, but it's through changes in meteorology, as well as changes in natural emissions, changes in movement of air from place to place. Third, I'll talk about this as well. So the sources of air pollutants and greenhouse gases are shared, and they're mainly in fossil fuel combustion, so that if we take action to reduce emissions of one type of pollutant, we might very well at the same time be having a benefit for the other. And finally, that climate change may influence demands for energy and therefore for emissions. So my lab has studies on all four of these types of interactions, but I'll focus on number 2 and number 3 here. So the effect of climate change on air quality. Here we're using, again, this is Raquel Silva, but her work using model simulations that were performed for the IPCC. And in this experiment in particular, they're singling out the effect of climate change on air quality. We took those fields and then assessed what they mean for human health globally. So this is the effect on ozone with different signs from different models, but the net effect is detrimental here, but with a big uncertainty around it. For particulate matter, again, there's different signs, but only one model now says beneficial effect of climate change on PM-related deaths. Most say it's detrimental. And the number here is pretty big. So 200,000 or so deaths in 2100 attributable to climate change. And where are those globally? Well, they occur all throughout the world, though not uniformly, but we've estimated here that climate change is expected to make air pollution related deaths worse in each continent except Africa. Okay, let's look now at the effect of the fact that greenhouse gases and air pollutants share common sources, which I think is a more important link, which is, and I'll put that in the context here of co-benefits. So if we're taking action to reduce greenhouse gas emissions, those actions will likely reduce air pollutant emissions from the same sources. So if we move away from coal-fired power plants to natural gas or renewables, that's a win-win for climate as well as a win for air pollution. We're bringing down then air pollution, and that has a beneficial effect on human health. This pathway happens immediately, so soon after the policy or action is put in place, and it has the effect mainly locally to where those emission reductions take place as well. There's a second linkage here by which, by reducing emissions of greenhouse gases, we're slowing down climate change, and we saw that climate change by and large has a detrimental effect on air pollution. So by slowing down climate change, we're slowing down that detrimental effect with a benefit for health. In this study then, we're doing for the first time using a global atmospheric model to assess co-benefits. And as well, for the first time, we're assessing the importance of these two pathways. And just to give you one outcome, we found that this pathway, immediate and local, is much more important than the long-term global pathway for benefits. So I worked with colleagues at Pacific Northwest National Labs who run the global energy and economics models that drive the scenarios known as RCP scenarios that are used by IPCC and other organizations. So here we have one of those. We compared here RCP 4.5, which we're using as a global climate policy scenario. Comparing that with its reference case scenario with no climate policy, we implement a global carbon tax until we get to this RCP 4.5 scenario. So the only difference here is a global climate policy implemented in the model as a global carbon tax. Here, the reference scenario has the world getting dirtier and then cleaner through time by and large. Of course, the story is different in different world regions, but it's the difference between the blue curve and the red curve that gives us the co-benefit. The co-benefits that we estimate in the near term by 2030 or so, 500,000 avoided deaths per year. By 2100, then that increases to about 2 million avoided deaths per year. So a pretty substantial benefit of the climate policy on global air pollution and global air pollution related deaths, here avoided deaths. What we did then was to assign a monetary value to those benefits. So this is the benefit using a high value of a life in red and a low value of a life in blue. Those benefits seem to be pretty substantial for several world regions and in the global average. I've compared that here in green against the cost of taking action. So it's the median and the range of different models. By 2100, we're moving up the cost curve and the different models disagree on what the cost would be. But even then, the costs, the benefits are going to be comparable to the costs. Whereas in 2030, the benefits far, far outweigh the costs, because many of the first actions we would take would be to move away from coal as an energy source. Prior to our study, what's shown in yellow here is the full range of values in the global literature. And we had estimated, obviously, higher estimates than many studies that were out there. And one of the reasons why we got higher estimates is that we're using a global model now. So we're accounting for not only the effect of actions locally to improve air quality, but the effect of those actions to improve air quality elsewhere in the world, where a large population than the rest of the global population is exposed to that. I'll mention as well that Yuchang Zhang, a graduate student working with me, did a further study where he took those co-benefits and downscaled them to the United States. And what he found was that 85% of the avoided deaths in the United States for PM 2.5 come from domestic reductions, but that's not true for ozone. For ozone, we have a longer lived pollutant, so more of a foreign influence. And we have this effect of methane. So the methane reductions have an important influence as well that happens at a global scale. So 62% of the avoided deaths happen from foreign and methane reductions. Okay, back to our big story. So we showed in that last study that I just showed you that by reducing greenhouse gas emissions, we can have pretty substantial effects on benefits of reducing air pollution and reducing air pollution related deaths. If we ask the opposite question, what is the effect of actions to improve air quality on greenhouse gas emissions? We see that there's not such a strong linkage there. So, all we have to do is look historically at what happened. So this is from the US EPA looking historically at the decline in emissions here of many different pollutants. I told you this story by and large before. And we see that CO2 increased over this period as well, over the same period. So how have we gone about reducing air pollutant emissions and concentration? It's been through smokestack controls on large industry and electric power generation. It's been through motor vehicle exhaust controls. It hasn't been by people driving less. It hasn't been by people using less electricity or consuming less products. And it hasn't come about through switching to cleaner sources of energy. It's been by and large through smokestack controls, though in the most recent years here, we know in the United States that we're slowly, actually pretty rapidly closing coal-fired generation and moving away, but that's not entirely because of, that's mainly for economic reasons and not because of clean air regulations. If we look at China as another example, this is a paper by Bo Zhang, this is showing the really actually very rapid decrease of SO2 emissions, cutting them by half in China over the course of a few years. But even with these air quality improvements driving emissions down, CO2 went up over that period. Okay, so again, these are disjointed from one another. And another study, this is Yang O, who was my graduate student. He used a energy economics model for the United States and put into it a reduced form atmospheric model so that we could look at air pollution related deaths within that energy economics model. Then he turned the problem around to ask the question, what is the most cost-effective way to reduce air pollutant emissions and concentrations for the purpose of improving, reducing PM-related deaths in the US? And what he identified are some actions addressing particular sectors shown here But these actions which reduce PM 2.5 here, emissions, and SO2 emissions pretty substantially, had very little effect on CO2 because they weren't fuel switching actions by and large. I'll end here, but leave you with a bit of a different note, which is to say that this picture is changing and it's changing rapidly. And the reason why it's changing rapidly is because of the rapid drop of solar energy costs. So these are costs of of generating electricity in North America. Of course, it matters where you are within North America, but taken as a whole as a continent, this is the result. Where nuclear is here, coal is now not very cost competitive, natural gas is cost competitive, but the big story here was the reduction in wind generation cost, and especially this really dramatic reduction in solar generation costs. And of course, to implement it at utility scale, you also need storage, and those costs are coming down as well. So as a result of this, though we've historically preferred to use smokestack controls rather than cleaner energy sources to bring air pollutant emissions down, looking to the future, we think it might be more feasible that these worlds of climate mitigation and air pollution mitigation are sort of coming together through time. And they're coming together because of this falling cost of renewable energy. So I'll conclude here. So first, air pollution has been a 20th century plague that continues to today. And even though some areas of the world are getting better in terms of air pollution, others are getting worse and will continue to get worse for several decades to come, with substantial, as we've shown, effects on human health. Taking action to reduce greenhouse gas emissions will bring benefits to air quality and health that we've shown can exceed the cost of the actions in the first place, apart from obviously other benefits that you would get from slowing down climate change. Historically, we've seen that for the purposes of addressing air pollution, we've preferred smokestack controls, and that those actions by and large have had little effects on CO2. So when we look to the future, then it's the falling cost of renewable energy makes climate mitigation more feasible. And if we follow that pathway, rather than the pathway of smokestack controls, we're going to see not only that we solve this globally important problem of climate change, but we'll do it with substantial benefits for air quality and health. The cost structure of energy is moving in this direction rapidly. Really, the important question for us today is, how rapidly will these transitions happen? So thank you for your attention. I've enjoyed talking with you today, and I'll look forward to your questions when we're in the live session. I want to acknowledge our funding sources, and I want to acknowledge as well, especially the graduate students and postdocs that I've had the good fortune of working with over the past several years. So thank you for your attention. Bye.